In this video, we will discuss a third type of probability called compound probability. Compound probability, or a compound event, is the likelihood of two or more events occurring. This also can be written as a fraction, a decimal, or a percent of the total possible outcomes. Let's first discuss how can we calculate the total possible outcomes. Suppose you have 3 marbles in a bag, a blue, a purple, and a green. You randomly select a marble from the bag, put it back, and then select another. How many total possible combinations exist? The answer here would be 9. If you have 3 marbles in the bag, a blue, a purple, and a green, we know that if I take it out and put it back, then my second option for the marbles that I select could also be blue, purple, or green. So my choices are I could pick a blue and then another blue. I could pick a blue and then a purple, or a blue and then a green. I could also pick a purple and then a purple and then a blue, or a purple and a green. I could pick a green and a green and a blue, or the green and then a purple. That is 9 possible combinations. How would this change if you did not replace the first marble before selecting the second? This would actually leave us with only 6 possible combinations because we would no longer be able to get 2 blues, 2 purples, or 2 greens in a row if we did not replace them in the bag. To find the total possible outcomes, you can draw a tree diagram. You can make a list like I just did in the last example. Or we can multiply the number of outcomes for each event. Let's take a look at an example. If I tossed a coin 3 times, how many possible combinations would there be? I could draw a tree diagram showing that my first toss could be either a heads or a tails. If my first toss is heads, when I toss again, I could land on a heads again, or I could land on a tails. That creates 2 branches off of my first option. I could also, if I flip a tails first, flip a heads or a tails on my second toss. So far that's already 4 possible outcomes. Heads, 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 tails, tails, heads, tails, tails. But we still need to incorporate the third toss in there. So if I had heads the first toss, heads the second toss, my third toss could still either be heads or tails. If I continue that idea through my other options, you will find that I have a total of heads, 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 1, heads, heads, tails, 2, heads, tails, heads, 3, heads, tails, tails, 4, tails, heads, heads, 5, tails, heads, tails, 6, tails, tails, heads, 7, and tails, 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 8 possible outcomes. Now that can take some time. Same with writing a list like I did in our first example, can be time consuming, and it's possible that you might miss some combinations if you're not careful about making your list. So the third option that I mentioned is multiplying the number of outcomes for each event. Coin number 1 has 2 possible outcomes, heads or tails. Coin toss number 2 also have 2 possible outcomes, heads or tails. Coin toss number 3 will also have 2 possible outcomes, heads or tails. And to find the total possible outcomes, I can multiply 2 times 2 times 2, which is 8 total possible outcomes. That is much quicker. Now, while it doesn't give us what the outcomes are, it does tell us how many outcomes there are, which is typically all we need to know. Let's try a few more examples like this. Suppose you roll a die, flip a coin, and pick a card from a standard deck. How many possible outcomes exist? If you said 624, that is correct. 6 sides on a die, 2 outcomes on a coin, and 52 possible outcomes in a deck of cards is 624 possible combinations. A pizza shop has regular, thin, and deep dish crusts and 5 toppings: cheese, pepperoni, sausage, mushrooms, olives. How many different 2-topping pizzas can you order? Since there are 3 crust options and 5 topping options, we would multiply 3 times 5 times 5, which would give us 75 total possible combinations. This is also assuming that your second topping could be a repeat of the first topping. So that would be cheese and then extra cheese or extra pepperoni. If you did not want to repeat your topping for your second option, then there would only be 4 options. That would mean that instead of 75 possible outcomes, we would only have 60. You must create a new passcode for your phone. Your passcode can be up to 6 digits long, including numbers 0 through 9. How many total possible passcode combinations exist? If you said 1 million, you would be correct. There are 10 digits, including 0 through 9, for each space in your passcode. There are 6 spaces in the passcode, so that is 10 times 10 times 10 times 10 times 10 times 10, which is 1 million possible combinations. Let's take a look at how this translates into calculating the probability of something occurring. As we talked about in the first intro problem with the marbles, depending on whether you are replacing a set of marbles in the bag or not can affect how many possible outcomes there are. If you do replace them, that is an example of an independent event. The outcome of the first event does not affect the outcome of the second. For example, that could be like 2 completely independent things like flipping a coin and rolling a die where one has no effect on the other. But it could also be like the example where we picked the marble, replaced it, and then picked again. Dependent events are when the outcome of the first event does affect the outcome of the second. This would be like the example where we picked the marble but did not put it back. To find the compound probability, we are going to find the probability of event A, the probability of event B, and then multiply those 2 probabilities together. Similar to how we just found the possible combinations, although in this case we'll be writing the probabilities as fractions, how many times something occurs out of the total, rather than just multiplying the total possible outcomes. Here's an example of an independent event. You and your sister are playing a game. She needs to roll a 6 for each of her next 3 turns in order to win the game. Find the probability that she will roll a 6, and then another 6. Since there are 6 sides on a die and only one of them is a 6, we would multiply 1/6 times 1/6 times 1/6, giving us a probability of 1 out of a 216 chance that your sister will get those 3 6s in a row. Here's another example of an independent event. 1 marble is drawn from a bag of 20 marbles and replaced. Find the probability that you would select a green and then another green. Since there are 5 out of 20 greens, that is a 5 out of 20 chance of picking a green, putting it back, and then another 5 out of 20 chance of picking a green again. I would highly recommend in this case simplifying our fractions before multiplying them so that it makes our result in simplest form. So that's a 1 out of 16 chance of picking a green and then another green as long as the first marble is replaced. An example of a dependent event is the same scenario, only we are not replacing that first marble. So we know that there was a 5 out of 20 chance of picking that first green. Assuming the marble we pick is a green, there are now only 4 greens left, and there are only 19 total marbles left in the bag. The probability of picking a green and then another green without replacing the first is going to be 20 out of 380, which is a 1 in 19 chance.